Hi everyone. Somebody just recently asked me a question about a video I did on this question a few months back, and they made the excellent point actually, and I completely agree with them that in part two, A of k is actually definitely a polynomial of degree four. It's the or less is kind of superfluous, really. I think, and I just wanted to mention this right at the start, I think it's because the approach which they thought that candidates would use only guarantees that it's degree 4 or less. The stronger result, where you do actually calculate A of k explicitly, which is what I'm going to do in this video actually, because I think it's probably the easiest way to get the marks, it demonstrates that it's definitely a polynomial of degree 4. So whoever pointed out the poster, well played. Yeah, I completely agree. I think that's the case. And just to clear up any confusion that you might have, I think the reason why they've asked for degree 4 or less is simply because of the approach that they thought the candidates would use. It's not because it actually is, the poster is absolutely right. Can't remember who said it now. Arc Seller. Yeah, I completely agree. So yeah, there we go. But yeah, let me have another go at explaining this because I looked at the video and firstly I was horrified to see me muddle up the limits. I mean, come on, muddling up the limits. That's a bad mistake. So I just wanted to fix that really and have another go at explaining this question because it's really quite an abstract question and it's a good question though. It really is. It's all about functions. Now before I start, let's talk about function transformations. Yeah, let's talk about function transformations just before we actually do anything with the question. Function transformations, yeah, graph transformations I'm talking about here, where you want to reflect in the line x equals a, yeah, because it's well worth talking about this. How do we reflect in the line x equals a? Well, let's say you were reflecting in the line x equals 2, yeah, and I explained this on the last video, and let's say you had a little flag here, like, which looks something like that. Oh, this is terrible. Let me do it on GeoGebra. I think it'll be better on GeoGebra. 1 second. Let me just put it across the screen. So let's say we had a little flag like this. Zoom out a bit. If we wanted to reflect that in the line x equals 2, let's put the line x equals 2 on here. Okay, and then let's just make it look a bit nicer. 1 second, won't take a moment. Cool. Okay, so there's a line x equals 2. Everybody knows where that flag's going. Obviously, it's not exactly difficult to see. It ends up here. Now, how can we do this using the transformations that we're already aware of? Reflecting just x and y axis and translating. Well, what we could do with this flag to take it to there is we could reflect it in the y axis, where it ends up there. And then we could move it double the distance it is away from where from the line x equals 2. In other words, because you've actually first reflected it and sent it far away in that direction in the y-axis, because that's a gap of 1, that's now going to be a gap of 2, and therefore you're going to have to move it 1, 2, 3, 4 places to the right. If you see what I mean, that's always going to be double the line x equals 2. And that's why, I just wanted to quickly show you that's why the best way of thinking about these function transformations, or I mean, not the best way necessarily, there's lots of other ways of thinking about it, but the way I think about it is, I think if I want to reflect in the line x equals 2, then what I could do is I could reflect in the y-axis, yeah, and then translate 4 to the right. Now, how do you translate 4 to the right? Well, you replace x with x minus 4, yeah, to move it 4 to the right, yeah, and that's going to give you f of 4 minus x, yeah. Now, in general, yeah, so let's translate by vector 4, 0. Yeah, in general, and definitely you want to know this before you go in, to reflect in the line x equals k, f of x is going to become f of 2k minus x, yeah. That reflects anything in the line x equals k. That's a really good thing to know, actually, for any of the extension papers that you're doing. It's really, really useful. It's come in useful lots of times on math. It's helped me on STEP before as well. It's an interesting way of looking at symmetry. A little question for you, which you can think about. How would you do the same thing for the line y equals k? Yeah, how could you do a very, very similar trick for the line y equals k? If you can find a general result for that, post it in the comments below the video. Okay, so let's get on with a question now, because that's going to come in really handy for me when I get to part 3 and part 4 and part 5, I think, to some extent. Okay, so let's do this. What have we got here? We've got, an integral of a cubic. We're trying to find this area. We want to write down the area in terms of two integrals. Well, if I could get this right this time, that's why I was horrified. It's like, what I need to do is I need to integrate from 0 to k, x minus k, x minus 2. And you could just write down fk of x there. And then I need to add on the next area, but the next area is definitely going to be negative, isn't it? If you found it as an integral, it would be negative, and therefore we're just going to take it away instead to make sure it gets added on. Now, the mistake I made in the last video was I had these limits the wrong way around. I had it at 2 there and k there, and that just didn't make sense to me. I was looking back at the video, I was like wincing as I saw that. So there we go, that's all we need for that first bit. Okay, right. For part 2, definitely, if I was doing this in an exam, I'd be scratching my head thinking, what do they really want? Like, how much detail do they need in the answer? It's well worth actually looking at their solutions. What they expected you to do, 4 marks this is worth as well, was just generalise and say, well, actually what you've got is a polynomial of degree 3 plus k times a polynomial of degree 2. Why have we got that here? Well, if we look at what we were doing, if you actually multiplied it out, which is the way I'm going to do it, if you multiplied this out, what would you have here? You would have, think about this bit first, you're going to get x squared minus x times k plus 2 plus 2k, and all of that's going to be multiplied by x, if you see what I mean. Now, what that's going to give you is it's going to give you an x cubed, which is a polynomial of degree 3 in x. And then why is it a polynomial of degree 2 multiplied by k? Well, because you're going to get x times x there, which is x squared times by a k, and therefore you've got a polynomial of degree 2 in x multiplied by k. And that's why this solution works as it does. It's not a difficult way to do it. When you see how they've explained it, it's like, it's obvious. I completely agree with you. It's absolutely obvious. And interestingly, this is why they say, I'm certain this is why they say, prove that it's a polynomial of degree, a polynomial of degree 4 or less. Now, the fact is, as they state in the solutions here, and this is what I'm actually going to show, that a of k equals that, which is clearly a quartic in k. So I absolutely agree with you, Arcseller, that it's a quartic in, of degree 4 in k. But if you did their approach and you only did it as far as this stage, it's possible, if you didn't actually analyse it further, that could be a polynomial of degree 4 or less. And they were basically saying that we didn't want you to go into too much detail, just to show us it's a polynomial of degree 4 or less. But if you work it through, it's obvious that it's a polynomial of degree 4. It's definitely not less than that. So I just wanted to mention that. So let's actually work it through, because it's not difficult to work through. It really isn't. It doesn't take too long. We're going to have x cubed minus x squared k plus 2 plus 2kx dx minus pretty much the same thing, which is with these limits. The more I looked at this question, the more I thought, well, it doesn't take that long to actually, especially if they're giving you 4 marks. I mean, if only you knew that. But it says you're not required to calculate it, which kind of puts you off doing this step, but they would have accepted it if you did. And that's often the case, actually. I've seen A-level questions where exactly the same thing happens, where they say, oh, you don't have to do this, but they do accept it if you do it, and it's actually easy enough just to crank through the algebra and do it. It's not that onerous, really. Okay, so we're going to have x to the 4 minus x cubed over 3, k plus 2, because k is just a constant, plus k x squared between k and 0, and then exactly the same thing between k up to 2. Plus kx squared between k and 2. Let's get the limits the right way round this time. Okay, so what does that come to? We're going to have, why have I not got my over 4 there? That is poor, isn't it? I mean, look at this. I just make so many mistakes nowadays. It's a joke. Okay, so what do we got? We've got k to the 4 over 4 minus k cubed over 3, k plus 2, plus k cubed, yeah, minus 0 if you like, but 0 throughout just gives you 0 because everything's been times by 0. So minus, okay, here let's be a little bit more careful. We've got 2 to the 4 over 4, which is 4, 2 cubed over 3, which is 8 over 3, k plus 2, and then we're going to have 4k. Then we're going to get minus exactly the same thing over here. So that's going to end up doubling it because it's a minus minus. So k to the 4 over 4 minus k cubed over 3, k plus 2 plus k cubed. So let's do this a sensible way. Let's actually just double, because you've got something, take away minus itself, yeah? In other words, something plus itself. That just doubles this first term. And we're going to have k to the 4 over 2 minus 2k cubed over 3, k plus 2 plus 2k cubed. Yeah, and then we've got this little, now let's actually simplify this. We're going to have 4, and then we're going to have minus 8/3 k. Oh, plus a 4k, well that's like 12k over 3, isn't it? And minus 8k over 3 plus 12k over 3 is going to be 4k over 3. Might as well simplify that now. Plus 4k over 3. And then we're going to have minus 16 over 3. We might as well simplify that with a 4 as well, mightn't we? As that's 4 is 12 over 3. When you take away 16 over 3, you're actually going to end up with minus 4 over 3, I think, because that's 12 over 3 minus 16 over 3, yeah, minus 4 over 3. So let's just simplify that right away. And yeah, I think I've got the signs right there. Okay, so let's try and write down our final answer. Now, we are going to have lots of k to the power of 4s here, because we're going to have basically a half k to the 4 minus 2/3 k to the 4, yeah? And a half minus 2/3 is going to be 3/6 minus 4/6, which is minus a 6, so it's minus k to the 4 over 4. And then what we got for the cube terms? Well, we've got minus 4k cubed over 3, then plus 6k cubed over 3. Well, that's plus 2k cubed over 3. Okay, have we got any k squared terms here? I don't think so. And then we're going to have a minus 4k over 3 plus 4 over 3. Okay, right, did I get that right? Let's have a look. 4 over 3 minus 4k over 3, 4 over 3 minus 4k over 3, and then plus 2k cubed over 3 minus k to the 4 over 6, plus 2k over minus k to the 4 over, oh, did I write, I'm sure I said 6, but then wrote down 4, and it's clearly, you know, so many careless errors. We're doing a half minus 2/3, and that's the same as 3/6 minus 4/6, which is minus a 6th, yeah. So apologies for that. I hope that makes sense. It's not that bad, is it, really, just cranking through the algebra for that bit. For 4 marks, I think I'd feel more confident doing it. And it clearly is a quartic of degree 4. Yeah, absolutely. It's a, you know, it's a quartic in k. So yeah, it's a polynomial in k of degree 4. It's not less. Okay, part 3. Let's quickly run through this. I like these kinds of questions because it's just straightforward algebra. We're just verifying that that's true for any t. Well, f of k of 1 plus t, we just write down what it is because we already know what f of k of x is. Well, it's just this, but with x is replaced with 1 plus t's. So that's going to be 1 plus t minus k. And that's going to be 1 plus t minus 2, which is minus 1, and 1 plus t minus 2 is going to be 1 plus t, yeah, because we've got 1 plus t and we're taking away 2, so we're going to end up with minus 1 plus t. Okay, so that's f of k of 1 plus t. Now let's try and work out gradually the right hand side, yeah. Let's just point out that's the left hand side. The right hand side, Well, to work that out, let's just say consider f of 2 minus k of x first. Let's just write that down. F of 2 minus k of x is where, write down our original function, fk of x, so I can see it. Fk of x is x minus k, x minus 2. Okay, I can see it now. Okay, all I'm going to do is start with first, build it up slowly, swap the k's for 2 minus k's. So x minus 2 minus k, x minus 2. In other words, that's the same as x, and then we're going to have x plus k minus 2. We're going to have x minus 2. Cool. Okay, so that's f of 2 minus k, but of x. So f of 2 minus k of 1 minus t. Well, we need to trade all x's for 1 minus t's. 1 minus t minus 2 is going to be minus 1 minus t plus k. And then 1 minus t minus 2 is going to be minus 1 minus t. Yeah? Okay, that's that one bit done. Now let's just multiply it by minus 1. So what am I going to do here? Well, I want to change it into, remember, this, yeah? So I'm happy to times this by minus 1, because that gives me the first bracket. Now, these two, I do actually want to change the sign, because if you look, that's backward. Oh, sorry, yeah, where am I here? Yeah, that's backwards, because I've got 1 minus t here, and that's t minus 1. And here the signs are all the opposite, isn't it? 1 minus 1, t minus t, k, minus k goes to a k. So really all we're doing here is we're timesing this by minus 1 and this by minus 1, which means it's not changing it because, we've times it by 1 overall, if you like. There's lots of ways of looking at that. So 1 plus t minus k, and then I'm going to have a t minus 1. So I've times that by minus 1, and I've times that by minus 1, which means I haven't changed the value of it, because I've, if I had a product, something like 6 times minus 2 times minus 3, if I times those by minus 1, obviously it equals 36. Well, that's the same as 6 times 2 times 3. If I change the sign on two things in the product, then it doesn't do anything to it. Okay, and hence, I might put right hand side equals here now. Hence, left hand side equals right hand side, and the result is established. Okay, right. Part 4, sorry. How can the graph y equals fk of x be transformed to the graph of y equals 2 minus k of x? Well, this is nice, isn't it? Because if I just use part 3's answer, but with a little substitution, knowing what I know about reflections in lines, yeah, I would just say, if I know that f of k of 1 plus t is the negative of f of 2 minus k of 1 minus t. This is trying to show you that there's some symmetry when you're reflecting in a line. Yeah, that's what it's trying to show you. And I do want to demonstrate this in a second. But what I did just a second ago when I was looking at this again was I thought to myself, well, if I let x equal 1 minus t, then obviously if I'm working this out, x minus 1 is minus t, so 1 minus x is t, and so 1 plus t is going to be 2 minus x. Yeah, then I can clearly see that f of k of 2 minus x is going to be the same as the negative of f of 2 minus k of x. Yeah, in other words, how are these two graphs related? Well, it's particularly obvious if we put the minus now on this side. And you can just say, well, if I want to get from, if f of 2 minus k of x is exactly the same as f of k after it's been reflected in the line x equals 1 and then reflected in the y-axis, yeah, then it's the same thing, isn't it? Yeah, that's the thing. So how are they related? Hence, the relationship is reflect in line x equals 1 and then reflect in the x-axis, because the y coordinates have changed from positive to negative. Yeah, if you like, all that's happened is, when we've gone, to get from f of k of x all the way to f to the 2 minus k of x, first thing you do you do it via this. You need f of k to become fk of x to become fk of 2 minus x. That's a reflection in the line x equals 1. And then you need to make it negative, and that's a reflection in the x-axis, and you get there. That's what we're really saying. Okay, so that's that one. That makes loads of sense as well, because what are we really saying here? Well, now I'm going to deduce this. Yeah, what am I going to deduce here? Well, what we're saying is, let me just get my graph over here. 1 second. I was doing this a second ago. Let me just get rid of lots of the things here. Oh, might even be better if I just start again. I don't know. Let me just try and unclip these. Go away. Have I got rid of them all yet? No, almost. Okay, and then I want that and that in. What's this doing here? Oh, there we go. Oh, no. Undo. There we go. Okay, right. Here's the graph. I've just let k equal a half here because I didn't want it looking too symmetrical right on 1. I just wanted to show you this property holds for any value of k. So I've said k is a half, yeah? Now, if I was to replace k with the minus, of 2 minus k here, what happens? Well, sure enough, it ends up having reflective symmetry in the line x equals 1. Do you see what I mean? Now, I wanted to show you how this, shows that a of k equals a of 2 minus k. It's simply because the area has been reflected and then turned upside down, yeah? Reflected in the line x equals 1, which is halfway between 0 and 2. Yeah, that's why this one's now over here. And then if you turn that area upside down, well, of course, the area is going to be exactly the same. So, how am I going to explain this? It'll be interesting to see how they do it in the answers, actually. But quite simply, yeah, as we are just reflecting twice, the area is preserved. The area is preserved. And a of k equals a of 2 minus k. Yeah, that's just going to be the case. What are they saying here? Like, do they go into much detail about why that's justifying? No, it's literally just mentioned as a comment at the end. I think it's direct. They've just said because they've described it as a rotation, a reflection, and a reflection. It's area preserving. They just set it down like that. Good, because I would do the same thing. I would just say it's obvious now. Like I say, especially from GeoGebra, you can see we're just before we were dealing with this area up here and this area down here. Well, if you reflect that in the line x equals 1, you've now got this. And now, and then you reflect it in the x-axis, you're going to have exactly the same graph, and hence the area is preserved. Okay, so let's actually do the last bit. Now, the last bit, yeah, I had a sort of clever argument here. I kind of thought about it like this, which is very similar. They've got a much better way of doing it in the mark scheme as normal, but this is the way my brain worked. I was kind of like, well, okay, I know a of k is quartic, so I said, we know all expressions for a of stuff, if you like. Yeah, we know a of stuff is quartic. Let me just write that down first. A of stuff is quartic, guaranteed, and it's not less than or equal to quartic. It's quartic. And so let's consider a of u plus 1. Yeah, and let's write it down as a quartic as like little a u to the 4 plus b u cubed plus c u squared plus d u plus e. Yeah. Okay. Now let's use the property we've just shown, that a of k is a of 2 minus k. So as a u plus 1 equals a of 2 minus u plus 1, yeah, which is of course a of 2 minus 1, which is 1, and then we're going to get 1 minus u, yeah. We can then therefore say, hence, a of 1 minus u Well, what's that going to be equal to? Well, let's have a look at this, and what's happened here. We've replaced u with a minus u, haven't we? Because this is 1 plus u and this is 1 minus u. So we can say this is the same as a minus u to the power 4 plus b minus u cubed plus c minus u squared plus d times minus u plus e. Yeah. And as we can see, this obviously, we already know it's the same as that. Yeah, let me not even bother with the brackets here, because I wrote it down up here. It should equal a of u plus 1. Yeah. Well, just by comparing coefficients, we can see this can only be true if b equals 0 in my case and d equals 0. Yeah, because the other terms are going to be identical. You're going to have au to the power 4, same as this one. You're going to have cu squared, same as that one. You're going to have an e on the end, same as that one. But these are going to have different signs, and that's going to be only the case if b equals 0 and d equals 0. And so I can say, so au plus 1 must be able to be written as au to the power of 4 plus cu squared plus e. Yeah, but if we let u to the plus 1 equal x, set it equal to x, then this is going to be, oh sorry, k is it they want us to show. Let u plus 1 equal k, and then we're going to have ak equals a k minus 1 to the power of 4 plus c times k minus 1 squared plus e. Yeah, and we've proved their result. Yeah. But yeah, it's essentially about the powers here, and you're essentially just showing the symmetry, you're just using that result above to show that that's the case. And they didn't ask us to calculate them explicitly, which is interesting. So yeah, there we go. That's my slightly, maybe only ever so slightly improved attempt at that question. Remember, when I'm doing these papers, I'm not claiming that I've got a brilliant answer. I'm not claiming that my answers would score full marks. And I fully invite everyone to comment and criticise and point out where I've made mistakes or anything like that. Please do. I will make mistakes. And even if it just opens up discussion of how we handle these incredibly difficult questions, I think that's a good thing. I really do. So yeah, I look forward to hearing any comments that you might have, and please, do criticise if you think criticism is warranted. Okay, bye bye.